Today's lecture will be on ice problems. We will explain what the principle behind an ice problem is and do an example ice problem. This is one of the shorter ice problems, is how we designate these in our class. The issue with the law of mass action problems that we have completed up to this point is that all the concentrations that have been given to you are concentrations that are already at equilibrium. Therefore, you could plug those concentrations directly into the law of mass action and calculate your KEQ value. The reality is it's very difficult for us to determine an equilibrium concentration because these gases or aqueous solutions are all mixed together in a closed container. So to separate those out oftentimes is very difficult. It is far easier for us to measure the initial concentrations of either the gases or aqueous solutions as they're being placed into your reaction container, and therefore do a calculation to determine what those equilibrium concentrations will be. That is the example that we have in front of us, the ice problems. We have shorter ice problems and longer ice problems. This is an example of a shorter ice problem. We've got an equation listed up on the board where all three species are in the gas state. You're given an initial concentration of PCl5 and an equilibrium concentration of PCl3, and you'd like to calculate KEQ. Because we are calculating KEQ, we know this to be what we call a shorter ice problem. First thing we're going to do is we are going to, as we've done before, use brackets to represent concentrations. We're going to list the three species as their own separate row, and then we'll have the initials I, C, and E. The initials I, C, and E stand for initial concentration, then change in concentration, and finally equilibrium concentration. So we get the abbreviation ICE from those letters, I, C, E. So now that we've got those terms defined, let's go ahead and fill in the information that we have in our chart. We have an initial concentration of PCl5 at 1.2 molar, and we have an equilibrium concentration of PCl3 at 0.56 molar. Now, there are two other pieces of information that we know, even though it's not explicitly stated within the problem. We have products. By definition, unless the numbers are specifically stated within the problem, you can assume that the initial concentration of your products are 0. So this initial concentration will be 0 molar, and this initial concentration will be 0 molar. There's no physical way to have a negative concentration. Concentrations start at 0 and are forced to increase. So if we have 0 concentration to begin with, the change for the product side has got to be positive. Because this is a closed container, if the product side is increasing in its concentration, that means the reactant side has got to decrease in its concentration. We don't know what that change is, so we're going to initially call that change just simply X. So we're going to have plus X on the product side and minus X on the reactant side. We end up with a rather simple statement here in our middle column at this point. That simple statement is 0 plus X gives me 0.56. That means that simply X is just 0.56. We call this a shorter ice problem because you're able to solve for X within the ice chart itself. So if we then apply that X to these different values, we're going to get 0.56 molar as our equilibrium concentration for Cl2, and then we have 1.2 minus the 0.56, and that's going to give me an equilibrium concentration of 0.64 molar. Now at this point, I'm ready to go ahead and write my KEQ expression. We're going to have KEQ equals the concentration of PCl3 times the concentration of Cl2 divided by the concentration of PCl5. I'm going to plug these values in, these three right here, into my KEQ expression. So we're going to have 0.56 times 0.56 0.56 divided by the 0.64. And then that's going to equal our KEQ value. Go ahead and do that math with two significant figures, and we get a KEQ value of 0.49 as our answer for this problem. Once again, remember KEQ is a unitless number. It does not have units associated with it, and the KEQ value can tell you something about where the material can be found on the reactant or product side. When it is a really, really large number, that means your reaction is going to favor your products, and when KEQ is a very, very small number, your reaction is going to favor your reactants. As you look at these concentrations, they are very similar to one another, and that's why we end up with a KEQ value very, very close to 1.